All right, next we have Christian talking about plan. Floor is yours.
Thank you. Yeah, I'll be talking about our work, which we titled Plan, on variance-aware private mean estimation. And here at Petri, of course, know that privacy can mean many things. So specifically, when I talk about privacy in this talk, it'll be about differential privacy. And I'll just start out with some of the tools from differential privacy that are needed to follow this talk. So sort of informally, one of the ways we can achieve differential privacy is that instead of releasing some query output exactly, we'll add noise to the query. And the idea here is that the distributions should not depend too much on the individual on any individual's data. And I have a sort of a small example here where the true input will be either 0 or 1, depending on some of your sensitive data. And then if I can only observe the output after adding noise, then I can't be sure if it's from this red or blue distribution. And there are two concepts from the field of differential privacy needed for this talk. And one is that privacy in differential privacy is quantitative. So if we add more noise, then we get stronger privacy guarantees, simply because the distributions are then even harder to distinguish. And then the other thing is known as sensitivity, meaning that depending on how much the query can change also affects our privacy guarantees. So apart from this example with 0 and 1, there's another example where the true output is either 0 or 3, depending on the sensitive information. And now it's much easier to distinguish the distribution, but then we can mitigate this by increasing our magnitude of noise to get strong privacy guarantees again. And the problem we want to solve here is mean estimation. And the idea is that we're giving a data set of n data points, and they are encoded as some d-dimensional vector, where each vector corresponds to some features describing one individual. And then we assume that the data points are from some underlying distribution, and we want to estimate the mean. This is a common task in data analysis and in particular in statistics, where we don't assume that we can gather the information, the statistics of every individual, but then we use that to estimate something about the population. And if we don't have to think about privacy, then the typical way to solve this problem is to report the empirical mean. So we have this data set and we just report the average of all the vectors we have in the data set. And the question is, why is this interesting from a privacy perspective? Well, it's because the empirical mean can reveal some information about individuals if we sort of can track things over time, for instance. So here's a small example where the empirical mean is marked with a cross, and I have some data points. And then I, as an adversary, might know what the empirical mean is of my data set. Then someone else's data is included in the data set, and I observe the new empirical mean. And even though I only saw these aggregate queries, I can infer exactly what their input was, because now the mean moved a lot. And this is can be an issue if for outliers in the data set, that they will be easier to detect. So how will we mitigate this from a privacy perspective? Well, instead of releasing the empirical mean, we want to estimate it, and we'll be doing so by adding noise to every coordinate in this data set. Every coordinate of this empirical mean. And now our goal is to minimize the expected distance of our private mean to this empirical mean, while still satisfying the privacy constraints, of course. So what I want to present is more the core idea of sort of our technique compared to previous work. And we focus primarily on what we say are skewed distributions. So that would be some distributions where some coordinates vary quite a lot, while other don't vary very much. And here's sort of a simplified example in 2 dimensions, where we say that all data points come from this gray box. And one of the standard techniques in differential privacy is called the Gaussian mechanism, where we add the same or noise with the same magnitude to each coordinate from a normal distribution. And this is sort of visualized with this brown circle. And the problem for this kind of setting that we are interested in is that this technique adds way too much noise to the small coordinates. So remember from the previous slide that if coordinates differ a lot from adding an individual, we have to add more noise. But in this case, even though the y-coordinate doesn't really differ a lot, we have to add a lot of noise to it because the x-coordinate differ using this technique. And we get a particular error here. Don't worry too much about the particular error, but just know that the problem with this approach is that we add way too much noise to the small coordinate. So then an alternative technique we could use is to scale our noise proportional to each coordinate, so that we add more noise to the large ones and less to the small ones. And you can see here, if we scale linearly to how big the coordinates is, then we add way less noise to the small coordinates, which is great. Now the only problem here is that now we add way too much noise to the large coordinates. And it actually turns out for the error metric that we are interested in, that we get the exact same error as we did for the other ones, that everything we saved for the small coordinates we sort of paid for with the large coordinate. So our technique uses sort of a middle ground, which you can see by this blue ellipses, where we add less noise to the small coordinates, but we don't have to pay the entire cost for the large coordinates because we don't decrease it as much as the other approach. And this is sort of tailored towards our specific error metric. And this is sort of the core idea of what we do compared to what previous work has done. And in this simplified setting where everything comes from this box, the error now scales with what is known as the L1 sensitivity. And just to compare it to the two other approaches, we can say that it's never worse, but it will be better, and then how much it improves depends on how much skew there is. So if all the coordinates are roughly the same, then we'll perform roughly the same as the other techniques. But if there's a lot of skew, so we have a few large coordinates, then we can save quite a lot. So that's sort of the core idea that we use in our algorithm. And just want to go through sort of a very high level what is the ideas of how our algorithm works. So we start out by having the original data sets, and here the star marks the empirical mean, and which we cannot release due to these privacy reasons. And then our technique sort of recenters the data, so we get some rough estimates. I don't really have time to discuss the details here, but the idea is that we sort of move the data based on some bad estimates, but it allows us to add less noise later. And then we scale our data based on this approach from the previous slide, where we want to add less noise to small coordinates. Then the next step is to clip the data points to a certain length, and this is a very standard trick in differential privacy, because this allows us to eliminate outliers. If there's a single point that is very, very far away, then we clip it so it's much closer to the center. And then we add noise, sort of using a standard differential privacy technique to this new version of the dataset. And then we inverse all of these transformations that we perform to get back to the original location. And just there's of course much more technical details in the paper, and I encourage you to take a look if you're interested. Just a sort of a brief summary of some of the things that I didn't talk about here is that we look at on the theory side of things. We analyze the error on some sort of well-behaved distributions and give error guarantees depending on what kind of distributions we're working with. And then we perform a lot of experiments on both some synthetic data sets where we follow some of these distributions, and then also on some real data sets, and compare with previous works. And then we also analyze a more general error metric than this L2 error. And one of the key takeaways or key methods of our work is that the way we choose this scaling, where we prioritize either small or large values, that will depend on the error metric itself. So sort of the error we want to optimize towards is input to our algorithm, which is one of the a bit unique things with our work. And sort of the conclusion is that we outperform the previous state of the art when we have these distributions that show a lot of skew, and if they don't have a lot of skew, then we perform comparably to them. But that shows that it actually pays to take advantage of this skew for this problem. And that was all. Thanks for listening to the talk.
So we don't have that echo from before. There's already a question here.
Very nice work. So could you maybe formulate this as like a more, I guess, general optimization problem where like maybe given a certain data set, you can like look at what is the best noise to add to like every dimension and maybe like scale things and do things like this. But I guess the key point being that like your solution depends on the given data set that you're given.
Yeah, and I think so. One of the things is that it also depends a little bit on the specific problem. One of our key techniques is this is adapting to the error metric that we are working with, and the error metric that is relevant to optimize will depend a lot on the actual problem, right? And we don't. There are also some other error metrics that we don't consider, and if those are the important ones, then sort of our techniques doesn't apply as much. So the idea is to sort of my philosophy is that we have to have several different kinds of techniques that we can use, so that you can sort of choose a mechanism that works on your specific problem. And also some of our techniques, there are several different lines of work in this mean estimation. There's a lot going on with private mean estimation, and you sort of lie yourself on the scope from making no assumptions about data at all to assuming that data is from a very specific distribution. Typically it's the Gaussian distributions because it has a lot of nice properties. We try to lie a little bit in the middle. We don't need as strong assumptions that it's a specific distribution, but we want to see, okay, what can we do if we have some assumptions on the data set? Thank you.
Do we have more questions? Nothing? The next speaker can already set up while I'll ask a very quick one. No, you're not getting away already. So this is a pretty high-level question. Maybe I'm completely out there. But where does the data come from in the sense of does the adversary have any impact on introducing individual data points into the data? Right.
So here we abstract most of that away, but we assume that data is from some distribution whenever we analyze our error and things like this. But from a privacy perspective, we have to satisfy this privacy constraint even if it's an adversary poisoning the data set. So there is sort of this disconnect between the privacy analysis. You have to take a very worst case approach, and then if we want to say anything about utility, we need some assumptions that data look decent at least.
Cool. Thank you. Let's thank the speaker again.